Hey folks, we are going to learn about the greenhouse effect today, which is a very important concept in environmental science. It's probably like the biggest one of your generation, and it is notoriously misunderstood. So we're hopefully going to tackle some of those alternative misconceptions and just give you kind of like the nuts and bolts of how this process, which it is pretty complex. People always argue about it, but just kind of get the nuts and bolts on how it works. So, to begin with, let us look at the moon and the earth and sort of compare them simply in terms of their temperature. Because, well, the earth, we know its temperature, like you can live in it. Okay, it can get a bit cold, but by and large, it's pretty warm. If you compare it to the rest of the universe, it's quite warm. Now, the moon is just a wasteland. It is like negative 200 degrees Celsius when the sun is not directly shining on it. It is very cold. And we need to unpack, like, well, why is the moon so cold and the earth is kind of warm? They're both round. The earth is a lot bigger than the moon. This comparison is quite off. But they're both the same distance from the sun. Like, why are we getting this sort of weird effect? So we have a diagram here. We have our sun, and we've got our lovely moon. We'll forget about the earth for the moment. Let's stick to the basics. So the first thing to understand is that the sun has a lot of energy. It's a massive fusion power plant. It's generating massive amounts of energy. And that energy comes out in the form of electromagnetic radiation, which is a fancy way of saying light. Okay? And this light goes in all directions, up, down, left and right, towards the moon, away from the moon, that sort of thing. And when we draw these diagrams, we don't actually care about the light that doesn't hit the object that we're talking about. So first of all, get out of it. Go away, light. I don't see you, do you exist? Right? So this light is going to the moon, awesome. Now, this light, this electromagnetic radiation, it looks a bit weird. It is what's called a wave. And a wave has what's called a frequency and a wavelength. If you study physics later on, you will unpack a lot of these types of things. But for our purposes, we just need to know a few things. So, light comes in many different forms. On one end of what's called low energy light, you have things like radio waves and microwaves. And right on the far end, you might have something like gamma rays. If you get hit by a gamma ray, well, it's game over, man. Don't get hit by a gamma ray. And right in the middle, you've got what's called visible light. Now, visible light is the light that human beings can see. That's why we call it visible light. Some animals can see a little bit beyond visible light. So, for example, like bees can see in ultraviolet, and snakes can see in infrared. But we can only see invisible light. Okay. Now, for our purposes for understanding the greenhouse effect and some other things, we are only going to concern ourselves with these three pieces of light: infrared, visible light, and ultraviolet. Infrared is a type of light that transmits heat. Okay? Visible light, what we can see. Ultraviolet, how do I explain it? It's high energy and it's a carcinogen. It can destroy things. But yeah. So let's have a look. The other thing is when we are looking at these diagrams and we're drawing them, drawing a wave is sort of a bit of a pain. It also doesn't show direction. So we're going to use an arrow. Okay. And there's a few rules with these arrows. One is it shows the direction. Awesome. The light is coming from the sun to the moon. The other thing is that the size of the arrow indicates how much energy there is. And we're not going to be super precise about this. All we need to understand is that like a thin arrow means low energy. A big fat arrow means there's been some event on the sun, a solar storm, this huge amount of energy coming to the moon. And in the middle, life's pretty good. Okay. So this light comes from the sun. It comes to the moon. There's a few things that can happen. The first is that it is reflected. Okay, and this happens all the time. The reason that you can see the moon in the sky is because there's sunlight hitting the moon and it's being reflected into your eye. That's how you see things. And yeah, it's reflected. So we can see the light that's bouncing off. Okay. Another thing can happen is that the moon can absorb some of this energy. And when I say the moon, I'm talking about any object, by the way. But it can absorb some of this energy and it holds onto it for a period of time. It could be, well, don't really quote me on this, but when I say a period of time, I'm talking about like a second or two, maybe even less, maybe microseconds or things like that. It's not a huge amount of time. It holds onto it and then it re-emits it, okay? And it emits this as infrared radiation. And we'll color this red in these diagrams. Now, just to remind you, what is infrared radiation? It is heat. We feel infrared radiation. You can feel that as heat. You can't see it. But if you like stood in front of the sun, you would feel this infrared radiation. You feel its heat. Okay, so things can emit that infrared radiation when they absorb light. Okay, now it can go in all different types of directions. It's random in the direction this infrared radiation comes out. That's an important concept to understand. It's random. It goes up, down, left or right. So be it. Okay, so that's the moon. Now, the reason the moon is kind of cold is, well, this radiation has just escaped out into space. It's not holding on to it. So even though, like, you know, it heated up a little bit, well, then it just disappears, goes out into space. Nothing's holding on to it. Okay? So that's why the moon's really cold, negative 200 degrees Celsius. And we can combine this all as a diagram. The light's either reflected or it just goes out into space. Easy done. All right, let's get a bit bigger. Let's go to the Earth. Now, the Earth, it is bigger than the moon, but importantly, it has an atmosphere. And the atmosphere has a whole bunch of things in it. Okay, it's got nitrogen, it's got carbon dioxide, and the big one that we are going to focus on for the next couple of minutes is water. Okay, and I've represented that as clouds. Okay, so our sun is going to emit some light. Okay, and it comes towards the Earth. Now, some things happen. It can get reflected off by the clouds. Okay. Now we know this because if you're lucky enough to be an astronaut and you're in the International Space Station and you're taking a photo of the Earth, you'll be able to see the clouds. And the reason you can see the clouds on Earth is because the sun is hitting them, they're being reflected back to you. So we know reflection happens from the clouds, okay? Conversely, you can see the clouds from the surface because the sun reflecting on them, okay? Some of the light gets through. We know that because you can see. And some of the light can be absorbed by the clouds and it's emitted as infrared radiation. And it could be emitted out to space. It could also be emitted back to Earth. It's random which direction, okay? That's fine. This doesn't change the temperature of the Earth, just this part here. Because the light's coming into the Earth, it's just bouncing back. Energy in equals energy out. Well, there shouldn't be a change in temperature. Okay? However, if this energy hits the Earth and it heats a bit up, okay, the infrared radiation can come out. And some of it can escape straight out to space, but sometimes it might hit a bit of this water vapor in the air. Okay? And what that happens is, well, that water vapor is going to heat up. It's going to absorb that energy, that infrared radiation. And then what does it do? Well, it could emit it out to space, random direction, or it could emit it straight back to Earth. Okay? And if it hits Earth, well, the Earth warms up. Get more light in, infrared radiation goes in the cloud, comes back. Okay? And what's happened is that this water vapor, these clouds, these greenhouse gases, water is a greenhouse gas. It traps the heat it traps the heat around the Earth. It creates what's like a blanket around there. And this is a good thing. This is a natural thing. We have had greenhouse gases for a very long time. If you didn't have water vapor, right, which I think contributes like at least 90 to 95% of like the heat on the Earth, like the greenhouse effect. If you didn't have that, we would be in conditions like the moon. It would be inhospitable. So one misconception that people talk about is they say, oh, the greenhouse effect is really bad. Like it's an evil thing. No. Bro, you need the greenhouse effect. If you don't have it, this place, you can't live here. Okay. Now, and this is like sort of like a common diagram that you will see, and it just shows everything that we've put together, right? Sunlight comes in, it's a big fat arrow, some of it gets out, some of it's reflected, some of it's infrared radiation coming out of the cloud. Some of it hits the Earth, some of that escapes as infrared radiation, and some of that will hit a greenhouse gas and it's just bouncing around for a while, and it just keeps, that energy stays there for a while. And it's the same effect. If you put a doona around you, or like clothing, you feel warmer, not because the clothing is warmer, it's because it's trapped the heat there, right? So that heat comes out of your body, it hits your clothes, and it bounces back to you. That's why it feels warm. So it's the same principle. But it's a gas. And because you don't see gas, is it real? Who knows? Okay. And yeah, we call it the greenhouse effect because it's named after a greenhouse. Okay, this is a greenhouse. It's like a glass house. Well, it's usually glass. You can make it out of plastic or something. And these are good because they maintain like warm temperatures. So you could build these in like Northern Europe or Siberia. As long as they get a bit of sunlight, you can grow tomatoes there. So yeah, or if you see one in Melbourne in the botanical gardens, they always grow tropical plants there and things like that. And they can be very nice. You walk into it, and it's like you're walking in Queensland or something like that. So yeah, that's the greenhouse. All right. Now, I mentioned greenhouse gases. I said water vapor is a prominent greenhouse gas. It's not the only one. There are a few more. There's quite a lot, actually. But the major ones that environmental scientists at this level kind of think about is carbon dioxide. Okay. We have methane. Methane comes out of cows prominently, like when cows burp and stuff, methane comes from them. You can also get it from like swamps burning and things like that. A whole bunch of different things. And we also have ozone, O3. Okay. And the same effect applies to these things as previous with the water. So if I've got sunlight comes in, it hits the Earth, and we get sort of the infrared radiation coming out. It can hit these molecules, and it can bounce back to hit the Earth and warms up. There is a difference, though, between these particular greenhouse gases and, say, like water vapor as a cloud. These don't reflect light out into space, like at all. And it's because like they're too small and they're not like condensed as a cloud and things like that. And so there's a stronger effect in terms of like how effective they are as a greenhouse gas, because they're not bouncing that light out. The light all comes in, but they do absorb and then re-emit that infrared radiation, so they have sort of a warming effect. Okay, and that's still natural. It's still fine. Like these molecules have been around for a very long period of time, so there's nothing inherently evil about carbon dioxide or methane or ozone. They are part of the natural system and contribute to like a good climate, like not even a good climate, a livable climate on the Earth, and create sort of stable conditions for us to live in. Later on, obviously, like when humans really got underway, we have tinkered around with this, let's say, and there has been some changes to this, and this does have an effect. But we'll talk about that in another time about climate change. But at the moment, we're just concerned about the natural greenhouse effect. All right, more infrared radiation, why not? Now, let's talk about ozone. I made a big deal about ozone because there's an idea about ozone and how the greenhouse effect works. So, ozone is a greenhouse gas. Okay, brilliant. It also performs another special role. So, yeah, normal light just passes through. Most of the electromagnetic spectrum, I should say, passes through. There is a type of light, though, called ultraviolet light. This is the one I sort of brought up, roughly 10 minutes ago. And it's this one here. It's the high energy part of light. And it is very dangerous to human beings. It is the leading cause of skin cancer in the world. And you use for example, you use ultraviolet light to sterilize things. You could put water that's full of germs under an ultraviolet bed and it will kill everything. Well, I shouldn't say everything. Like some things can survive high intensity radiation, but by and large, it's very strong. So it has this really, really close wavelength. It's a very high frequency, very high energy wave, and yeah, very dangerous. And this is blocked by ozone. Ozone blocks it, and what we have here is what's called the ozone layer, and it is super important to the livability of our planet. Because if we did not have the ozone layer, we would be bombarded by ultraviolet radiation, and we would be in a huge problem. You wouldn't be able to go outside. It would be unlivable. And there's like, for example, like astronauts, if they go out into outer space, they have a lot of protective equipment. And one of the things is to protect them against this ultraviolet radiation, because there's no ozone layer if they're like outside in space. This is a gross example. Like the layer of the atmosphere is very thin compared to the size of the Earth. Now, what happened is that decades ago, people made refrigerators, and one of the chemicals they used to make these refrigerators is called CFCs. I think it's carbon fluorochlorines, chlorofluorocarbons, something like that. It's a complicated name, but what happens is those chemicals, it's a gas, it escapes from the fridge or the plant that's making the refrigerators, and they go up into the atmosphere and they destroy ozone. And what happens is you create this sort of weakness in the ozone layer around the Earth and allows more ultraviolet radiation in. And this is not a good thing, because people's life expectancy lowers. And this was a massive thing on the international scene. So they set up something that was called the Montreal Protocol, and they banned these CFCs, and every country on the planet sort of like signed up to that. I shouldn't say every country, I'm sure there's some that didn't. But we stopped producing them, and we have tried to fix the ozone layer. So if someone says like, well, the ozone layer is responsible for climate change or the greenhouse effect, what are they talking about? They're two completely different problems, okay? So one is about warming the planet, the greenhouse effect, and the other, the ozone layer, is about protecting living organisms from high intensity radiation. And this is sort of the ozone layer as it was, what was this, 2024? And like, you know, the yellow means it's high concentration of ozone, so these places are safe. And if you're in Antarctica in the summer, better wear some sunscreen, because it's not looking too good. Okay, and that's sort of the ozone hole. And there's other reasons why this is here. It's not just from CFCs, but that's, if you want to study atmospheric science, which, you know, can be a lot of fun, go for it. But yeah, other than that, peace out.